You ever wonder what it really takes to build an intelligent robot? One that can walk, see, and actually understand you? Not in a movie, but for real. Well, today we're going to tear that down because we're looking at the actual blueprint for building a thinking, moving, humanoid robot. And this right here, this sentence is pretty much the whole game. It's not just about building a machine that moves around. It's about creating something that gets what we want and can then figure out how to do it. That little gap between your intent and the robot's action, that's where all the magic and all the really hard work happens.
Okay, so to make this whole thing feel a little less like rocket science, we're going to treat this as our assembly guide. Think of it as the step-by-step blueprint for putting together a physical AI.
So this is the big question, right? If you tell a robot, hey, get me a soda from the fridge, what actually has to happen in its circuits and motors for it to pull that off? Believe me, it is way, way more complicated than you might think. All right, so here's the roadmap for our build. We're going to start with a nervous system, the thing that lets all the parts talk to each other. Then we'll give it a physical body. After that, we need to build its brain so it can see and plan ahead. And finally, we'll hook up its senses so it can actually understand us. So let's start at the foundation. Step 1. First things first. Before a robot can even think about thinking, all of its different parts need to be able to communicate. So we've got to build its digital body and the brainstem that's going to control all its basic functions. And that brings us to ROS2. It stands for Robot Operating System, but honestly, the best way to think about it is as the robot's central nervous system. It's the whole network of digital nerves that lets the brain talk to the arms, the legs, the eyes, and the ears all at once, totally in sync. So how does this nervous system actually work? Well, you can imagine that different parts of the robot, like its camera or an arm motor, are all individual communicators. They're constantly sending messages across shared channels. The camera is just broadcasting what it sees 24/7. It's this nonstop flow of information that lets the robot's brain process what's happening and react in a split second. Okay, so the parts can talk to each other. Now we need a body, and that is where URDF comes in. Just think of it as the robot's digital skeleton. It's literally a file that describes every single joint, every limb, its size, its weight, how it's all connected. It is the complete architectural blueprint for the robot's physical form. Now here's the really crucial part. This isn't just some 3D model you look at. The URDF is the master plan that links the actual physical hardware, the motors, the sensors, to the software that tells them what to do. Without this digital skeleton, the robot's brain would have no idea how to actually move its own body. All right, we've got a body and a nervous system. Let's get to the next stage. Now we've got to give our robot a brain. We need to give it a mind's eye that can actually perceive the world around it and, more importantly, learn from it. So how does a robot learn? I mean, you can't just build thousands of super expensive prototypes and let them fall over until they get it right. Instead, we use simulators. And NVIDIA's Isaac Sim is basically a hyper-realistic video game for the robot. Inside the simulation, it can practice a task millions of times, fail over and over, and learn from its mistakes without any real-world consequences. And the benefits here are just huge. The simulation looks so real that it can create perfect training data for the AI. This means the whole development process is just exponentially faster, it's cheaper, and most importantly, it's a whole lot safer than trying to teach a multi-million-dollar, two-legged robot how to walk around a busy lab. So after all that virtual practice, when the robot is finally ready for the real world, it needs to see. For this, it uses a technology called VSLAM. And what this does is it lets the robot use its cameras to build a 3D map of its environment and, at the same time, pinpoint its own location inside that map. It's literally how the robot gets its bearings. So once it has that 3D map of the room, it uses a system called Nav2 to figure out how to get around. And this isn't just about not bumping into the furniture. It's about calculating the smartest, most efficient path to its goal. This path planning, this is what turns a simple map into intelligent, purposeful action. Okay, so this is the final piece of the puzzle. And honestly, it's kind of the most mind-blowing part. We've got a robot that can see, move, and plan. So now, how do we get it to understand what we want? How do we connect our human language to its physical actions? This right here shows the massive leap we've taken. Old school robotics, you had to write tedious line-by-line code for every single movement. Now, with physical AI, you just say what you want in plain English. The robot does the hard work of figuring out the rest. It's a total game changer. So what's the secret sauce that makes this possible? It's something called a Vision Language Action Model, or VLA, and it really is the magic bridge. It takes in language, what it hears, combines it with vision, what it sees, and then it outputs the series of actions needed to get the job done. So let me walk you through how this works in practice. First, something like OpenAI's Whisper transcribes your spoken command into text. Second, a large language model does what we call cognitive planning. It breaks down a big command, like get me a soda, into smaller, logical steps. And finally, the VLA system takes over and actually executes those steps in the physical world. So let's zoom out and put all these incredible pieces together. We've built the nervous system, the body, the brain, and the senses. We've officially assembled our humanoid. And you can see right here how each of these parts is equally critical. You've got the ROS2 framework as the nervous system, the URDF as the physical body, the training in Isaac Sim as its brain, and the VLA models for interaction. You take away any single piece of this, and the whole thing falls apart. They all have to work together to create one single intelligent being. Look, if you take one thing away from all this, let it be this. We are seeing a massive, fundamental shift. We are no longer just coding robots to follow a script of commands. We are now building systems that can learn, perceive, and actually understand our intent. We are teaching them, not just programming them. And that really leads us to the final and most important question. For the first time ever, we are right on the verge of having machines that can truly collaborate with us in the physical world. The technical blueprint is here, so the real question now is, what are we going to build with it? What kind of future are we going to ask them to help us create?